If I told you there are oceans in our own solar system that have never seen sunlight, oceans that might still be warm, salty, and chemically alive, would you feel hope or dread? Tonight, you're not watching a video. You're in the lab with me, and we're going to audit the two most tempting, nearby, places to find alien life, Europa and Enceladus. And we're going to ask the only question that matters: what would count as proof? It's January. Outside the window it's black and quiet, and that way winter does so well, like the world is holding its breath. Inside, the lab lights are down low, because bright light feels like an insult to the kind of work that happens at 1:17 a.m. There's a mug next to my keyboard. The coffee is cooling in slow motion, the way every late-night decision cools, first with confidence, then with doubt. On my screen, a live telemetry window, old mission data, and a model I don't fully trust yet. You pull up a chair, not as a spectator, but as another researcher leaning in. And before we even say Europa or Enceladus, before we indulge the part of our brain that loves exotic worlds, we have to do something unsettling. We have to redefine a word we think we understand. Home. Most people hear habitable and imagine a blue sky, a temperate shoreline, plants, sunlight. But that's not a scientific definition. That's nostalgia. Science doesn't get to be nostalgic. Science has to be operational. What conditions allow chemistry to do the long, patient work of becoming biology? So here's the question that sounds like philosophy but behaves like physics. Does life require sunlight, or does life require something more abstract, something like a steady opportunity to do chemistry? Imagine, for a moment, that you were born under ice. Not metaphorically. Literally. A sealed ocean, roofed over by kilometers of frozen water. No sunrise. No stars. No moonlight. No concept of night, because it's always night. What would the universe be to you? Not a sky. Not a horizon. The universe would be an ocean, a ceiling, pressure, currents, heat leaking from rock, and chemistry. And then the human stakes hit. If life can exist in a sealed ocean, the universe could be packed with hidden biospheres, worlds that don't advertise themselves with green continents and oxygen skies. Earth becomes less lonely, and also less central. But there's a second stake, and it's colder. If these oceans exist and still don't produce life, then we learn something equally sharp, that liquid water and energy might not be enough. That habitable is rarer than we want it to be. Either way, these moons aren't just destinations. They're tests. Immediate, reachable tests. Now, to do this properly, we have to audit. That means we separate what's exciting from what's supported. We name the instruments. We respect uncertainties. We keep our wonder, but we don't let wonder drive the car. So let's step onto the evidence the way you step onto ice you're not sure will hold. Slowly. Listening. Feeling for cracks. First, Europa. Europa is one of Jupiter's large moons, and it has an almost offensive elegance. From far away it looks like a smooth, bright marble. Up close, it's a cracked shell, dark lines lacing across pale ice like the surface has been stressed, healed, and stressed again. Those fractures are not just pretty. They're a story. A story of motion. Of tides. Of a moon being kneaded by gravity. Europa orbits inside Jupiter's intense gravitational field. Gravity isn't just a force that pulls, it's a sculpture that can flex worlds. If Europa's orbit were perfectly circular, the pull would be constant, and the flexing would calm down. But Europa's orbit is slightly eccentric, and it's kept that way by orbital resonances, gravitational rhythms with neighboring moons. The result is a repeating squeeze. Over and over. Here's the metaphor that doesn't lie. Tidal heating is like bending a paperclip back and forth until it gets warm. You feel that warmth because the metal resists, microscopic structures shift, and energy turns into heat. Now scale that up until the paperclip is a moon hundreds of kilometers wide, and the bending is Jupiter's gravity. That flexing produces heat inside Europa, and heat is the enemy of ice. This is why Europa is on our list. Not because it's pretty, but because it has a plausible engine for keeping an ocean liquid beneath a frozen lid. How do we know there's an ocean if we can't see it? We do it the way you diagnose a body you can't open, by measuring how it responds. Gravity, magnetism, surface geology, chemistry. Gravity measurements can tell you whether a moon's interior is uniform or layered. If the mass is distributed in a way that suggests a decoupled shell, an ice layer floating over something dense and mobile, that's a clue. Magnetometer measurements. This is where it gets deliciously indirect, can detect induced magnetic fields. Jupiter has a powerful magnetic environment. If Europa contains a conductive layer, like a salty ocean, that changing magnetic field can induce currents, and those currents create their own magnetic signature. It's like watching a curtain move and inferring someone is behind it. Then there's spectroscopy, splitting light into its component wavelengths to identify chemicals by the way they absorb and reflect. On Europa's surface we see hints of salts and altered materials. That matters because salts don't appear by magic. They suggest interaction with water, maybe ocean material reaching the surface, maybe surface material being processed and transported. But Europa also lives in a punishing radiation environment. Jupiter's magnetosphere hurls charged particles like a storm of invisible bullets. That radiation breaks molecules apart and makes new ones, oxidants, reactive species, chemicals that, if delivered downward into the ocean, could become energy currency for life. And that brings us to a concept that sounds technical but is actually intimate, a redox gradient. Redox is the electron economy. Life, at its core, is a set of trades. One chemical has electrons to give, another wants to take them, and the flow of electrons is like a battery powering metabolism. On Earth, sunlight often charges that battery by driving photosynthesis. But in dark places, hydrothermal vents, deep subsurface environments, chemistry itself can charge it. So when astrobiologists say, habitability, they're not chanting a spell. They mean something specific: liquid water, energy, the right chemistry, and time. Time matters because complexity is slow. Evolution is patient. Europa might have water. It might have energy via tidal heating. It might have chemistry via surface oxidants and a rocky seafloor. The question is whether those pieces connect, or whether they're separated by an ice shell that's too thick, too stable, too isolating. Now, Enceladus. If Europa is a locked door with scratches around the handle, Enceladus is a door that's already swinging open, violently, beautifully, and without asking our permission. Enceladus is smaller, orbiting Saturn, and it should have been geologically dead. Small worlds cool quickly. They lose internal heat. They become quiet. That's the textbook expectation. But then Cassini arrived. Picture it, a spacecraft moving through Saturn's realm, sunlight thin and pale, instruments awake, the radio link back to Earth stretched across an almost obscene distance. And then it sees them, plumes erupting from the south pole of Enceladus, jets of water vapor and ice grains venting into space like the moon is exhaling. That moment changes everything because it turns the hardest problem in ocean world exploration into a gift. We don't have to drill. Nature is doing the drilling for us. Cassini flew through those plumes. Not once, but multiple times. And it didn't just take pictures. It tasted them. Mass spectrometers separated molecules by their mass-to-charge ratio, letting us identify water vapor, salts, organics, carbon-bearing compounds, and crucially, molecular hydrogen. Hydrogen, in this context, isn't just a molecule. It's a clue about the seafloor. On Earth, molecular hydrogen can be produced when water interacts with certain rocks in a process called serpentinization. That reaction can create chemical energy that microbes feast on. If Enceladus has hydrogen, it suggests active water-rock interaction, potentially hydrothermal activity. A warm, reactive interface between ocean and rock. Enceladus also shows salts in its ice grains, which implies that the water has been in contact with rock long enough to dissolve minerals. It's not distilled water. It's ocean water. So in our audit, Enceladus earns a rare classification, a natural sample return. The ocean is not merely inferred. It is physically reaching into space. But now the dangerous part: organics are not life. Methane is not automatically biology. Complex molecules can form without cells, without genes, without anything we'd call alive. If we get this wrong, we don't just embarrass ourselves. We misteach the public what evidence means. We turn science into a vibe. And that is the one thing I refuse to do. So what would count as evidence of life if we can't land, drill, or see the ocean directly? Not one molecule. Not one headline. Not one pretty graph. What we want is pattern disequilibrium, chemicals that shouldn't coexist in the same place unless something is constantly maintaining that imbalance. Life is a vandal against equilibrium. In physics, systems tend to relax, to spread energy out, to become bland. Life is the exception that keeps repainting the wall. We want isotopic ratios that look chosen, rather than random, like carbon isotopes biased in a way biology often produces. We want distributions of organics that repeat in suspicious ways, like families of molecules that suggest a metabolism selecting and processing matter. And we want, ideally, multiple independent lines of evidence. Because any single indicator can have an abiotic explanation. But several, aligned, start to corner the truth. Now let's slow down, because this is where the story becomes suspenseful. The screen fills with error bars. Model disagreements. Competing interpretations. This is the edge of understanding, where the data is real, but the meaning is still in negotiation. Start with the most emotionally important unknown, the ice. How thick is the ice shell on Europa? Is it thin enough for exchange, surface oxidants mixing into the ocean material rising to the surface? Or is it thick enough to isolate that ocean for millions of years, turning it into a sealed vault? Both are plausible. That's what makes it maddening. A thinner shell makes Europa more accessible and more chemically connected. It also increases the chance that surface-produced oxidants could reach the ocean, providing energy gradients that life could exploit. A thicker shell might protect the ocean from radiation and impacts, making it stable, but it might also starve it of surface chemistry. Then there's the ocean chemistry itself. Does Europa's ocean have the right electron economy? If oxidants from the surface are being delivered downward through cracks, melt-through events, or subduction-like processes, that's a powerful energy source. But the transport pathways are uncertain. The timescales are uncertain. The rates are uncertain. Enceladus has a different set of uncertainties. The plumes are a gift, but they're also a filter. What we measure in the plume is not necessarily a perfect snapshot of the ocean. Some molecules might be destroyed, altered, or fractionated as water rises and freezes. The plume is a messenger that can smudge the message. So we have to be careful. But we can still design measurements that move the probability needle. We can plan an investigation that doesn't just collect cool stuff, but answers specific questions. Let's do the thought experiment together. And don't treat this like a game, because this is what mission design actually feels like: trade-offs under constraints, decisions with consequences. You're allowed one flyby, one instrument, 1 hour of data. What do you pick? A magnetometer to map the ocean's conductivity and thickness, because if you can constrain the ocean's depth and salinity, you constrain its habitability. A mass spectrometer tuned for amino acids and complex organics, because if you catch certain patterns, you might see chemistry that looks curated. Or a dust analyzer that reads ice grains like time capsules, extracting not just composition but structure, perhaps even hints of cell-like compartments, though that's the most dangerous territory for false positives. If you choose the magnetometer, you're betting on context. Learn the ocean's properties and let future missions do the biology. If you choose the mass spectrometer, you're betting on direct biosignatures, risking ambiguity. If you choose the dust analyzer, you're betting on something almost too good to be true. My answer, tonight, in this January lab, with that cooling mug and the quiet outside, is that for Enceladus, you take the mass spectrometer, but you design it like an investigator, not a tourist. You prioritize isotopes. You prioritize molecular families. You prioritize sensitivity and contamination control. Because Enceladus is handing you ocean material in flight. For Europa, I'm torn in a way that feels almost personal. Because Europa is the place where context might be everything. If you don't understand the shell, the transport, the ocean's interaction with rock, you can misread every chemical whisper. So for Europa, the magnetometer and radar, mapping structure, mapping thickness, mapping exchange, become not boring preliminaries, but the key to interpreting any future detection claim. And then, this is the realization that lands like a weight and a wing at the same time. Enceladus is not just a world. It's a venting laboratory. Nature is doing the drilling for us. Europa is not just a moon. It's a chemically charged ocean potentially interacting with a radiation-forged surface. Two different doors into the same question: can chemistry become biology under a lid of ice? At this point, the temptation is to jump to, so are they the best places to find alien life close to home? And answer with a confident yes. But confidence is not the same as truth. So here's the audited answer. They are the best places close to home to run a clean test. Not because life is guaranteed, but because the requirements we can name, water, energy, chemistry, time, are plausibly present. And because the evidence channels are real: induced magnetism, gravity signatures, surface geology, plume sampling. But whether they are the best places to find life depends on a brutal detail: whether those ingredients actually meet. Think of habitability as real estate that doesn't pay rent in sunlight. It pays rent in gradients. Differences in temperature. Differences in chemistry. Differences in electron availability. Where there are gradients, there is potential work. Where there is potential work, there is a chance, just a chance, that matter can learn a new trick and begin to maintain itself. And now we come back to the human scale. It's still January. You can feel the year ahead like an unopened notebook. In the lab, you notice something almost embarrassing: your own New Year resolutions are gradients too. Attention is a resource moving from chaos to structure. Time is a resource moving from possibility to history. Energy is a resource you either waste as heat or concentrate into meaning. The search for life under ice isn't separate from us. It's a mirror. We are also islands of order in a universe that prefers to spread out and cool down. If life exists under the ice of Europa or in the ocean of Enceladus, it reframes the habitable zone as a small subset of a much larger reality. The universe may favor hidden oceans over open continents. There could be more homes in the dark than in the light. If life does not exist there, despite oceans, despite energy, despite chemistry, then we learn a different truth that is just as profound: that life requires additional hard conditions we haven't named yet. Perhaps the right catalytic surfaces. Perhaps the right stability. Perhaps rare historical accidents. Perhaps timescales longer than these oceans have had. Either answer rewrites our understanding of common and rare. And then there's the ethical weight, which is not optional. If we go sampling, we have to sample without contaminating. Exploration cannot mean rewriting someone else's biosphere with our microbes, our chemistry, our assumptions. The cleanest discovery is the one we don't taint. So here's the synthesis, in plain terms. Europa and Enceladus are not fantasies. They are physical systems with evidence-backed oceans, powered by tidal heating, shaped by geology, and rich with chemical possibility. Europa offers a vast, potentially global ocean with a surface that may be feeding it oxidants forged by radiation. Enceladus offers direct ocean material in plumes, with salts, organics, and signs pointing toward water-rock reactions that could power metabolism. But the frontier is real: ice thickness, exchange rates, ocean composition, and the ever-present risk of false positives. The next step isn't louder speculation. It's better measurements, designed to discriminate life from chemistry with multiple independent checks. Now a thought to carry with you. Close your eyes and imagine a living thing that has never known a horizon, only a ceiling of ice. It doesn't dream of the stars because it has no word for star. And yet it may still sense gradients the way you sense hope, as a direction, as a difference, as an invitation. And the next great question, the one that opens the next door, is this. Are we searching for aliens, or are we searching for a deeper rule about how matter learns to live? If you want to keep going, click the video on the end screen, because it's the next step in this investigation, and it will change how you interpret everything we just discussed. And if you're not subscribed, subscribe for one reason: every episode here is built like an audit: claims, evidence, uncertainty, and the human meaning underneath it, so you never have to choose between wonder and rigor. One question for you, and it's easy to answer: if you had to bet on one, Europa or Enceladus, Which do you choose, and what single piece of evidence would make you change your mind? Final image: a spacecraft silhouette against a cracked ice horizon. Not fireworks. Just first light. The feeling that a new chapter in the solar system is opening, and we're finally reading it carefully.